One application of derivatives that you saw in Calc 1 was optimization. In other words, we took a function of one variable and found the value of the variable that gave the maximum or minimum value of the function. Can we do the same thing with a function of two variables? Now, as you probably guessed from even bringing it up, the answer to this question is yes. However, it will be a little trickier this time because there is no analog to the first derivative test that we saw back in Calc 1. Instead, we are going to talk about a version of the second derivative test, and even that will be a little bit more complicated than it was in Calc 1. So let's just start with a definition. So we have a function of two variables, in this case f, and we say it has a local maximum at a point AB if all points near AB have lower value. If f of xy is less than or equal to f of AB. And really the main point here is what's in brackets. If we were to draw our point, if we have an AB here, what we're saying is that there is some disk, a disk being the interior of a circle around that point, centered at that point. So for every single point inside that disk, the value of the function is at most as big as the value at AB. And this doesn't say how big that disk could be. It can be a really small one. It can have a very small radius, and that would still make it a local maximum if that is still true. Of course, we have the opposite of being a local minimum, just being that the values of the functions are always bigger than or equal to the value of the function at AB. Okay, so let's actually look at an example of this. We'll just kind of steal the book's example one, though we'll work with it a little bit differently than they did. But they have a function f of xy equal to x squared plus y squared minus 2x minus 6y plus 14. And we're going to graph this. So we have f of xy, again, it's x squared plus y squared minus 2x minus 6y plus 14. And maybe I'll move this down a little bit so you can see more of it. I want to keep those axes though. But we have a paraboloid, a very nice paraboloid. And the book actually even tells us the vertex of that paraboloid, and this is actually something we could find from completing the square if we prefer, just because we are working with quadratics here. That point is 1, 3, 4. It's a point right at the bottom of the paraboloid. It's pretty clear that this vertex is a local minimum for the paraboloid. If we were to take points near 1, 3, all the values of the function is above it. That's what we mean by a local minimum. Let's look at cross sections of this surface through this vertex that are parallel to the axes. So if we look at the plane x equals 1, we have a cross section. We could intersect this with the surface, and we get a curve. And one thing to note is that on that curve, this point still is a local minimum of that curve. If we look at the other direction, so instead of parallel to the y-axis, we look at the plane y equals 3. Again, that cross section has the point 134 as a local minimum of that curve. Now, say the wrong thing there. If we were to take another point on this surface, say 2, 4, 6, and look at cross sections through there, So maybe let's look at it. Yeah. Actually, let's look at, instead of that one, let's look at 2, 3, 5. Here we go. We have another point on there. We could look at the cross sections through that point. If we look at the cross section using the curve x equals 2, we can see that point is a local minimum of the curve made by that cross section. We still have our parabola, and we still have that at the vertex of that parabola. But if we look at the cross section in the other direction, which is actually the same plane as we had through our vertex, this point is no longer a local minimum of that cross section. And so that's kind of the key feature here, is if something is going to be the local minimum of a surface, it's going to have to be a local minimum no matter what cross section we take. In fact, it's going to have to be a local minimum for even cross sections that are not parallel to our axes. So that's the main idea we want to use. We can identify whether or not a function of one variable has a local minimum or local maximum by finding what we call critical points of it. And we find those critical points back in Calc 1 by looking at the derivative and seeing where the derivative equals 0, or if the derivative doesn't exist. But we'll return to that in a moment. But what we're saying here is if we take the cross sections in both the x and y directions, basically we look at the partial derivatives of the function, they have to give 0 for the exact same reason that they had to give 0 back in Calc 1. And so if f has a local maximum or minimum at AB and the partial derivatives do exist, then those partial derivatives both have to be 0. Note that this also is equivalent to saying that the gradient of the function at AB is a 0 vector, because this is just the vector made up of these two values. We're going to say that a point where the partial derivatives either don't exist or they both do exist and equal 0, like we have here, we're going to call that a critical point. So either one of these does not exist, or 2, both of them do exist, and they're both equal to 0. We call that a critical point. But of course, not every critical point is going to result in a maximum or minimum. That wasn't even true in Calc 1. We can wind up in a wide variety of situations. So just as some examples that I'll go ahead and graph for us, we could look at something like f of x, y is equal to x cubed. Now if we looked at the function x cubed back in Calc 1, this function actually does have a critical point at 0, and it does not have a maximum or minimum at all. So just kind of as a reminder what that looks like, we have this curve that just keeps going up. It never turns around or anything like that, but it does level off, actually have a horizontal tangent line at 0, enough that we see a critical point there, even though there is not a maximum or minimum. In the case of our function of two variables where we don't even have a y, we just have the x, it's actually going to be a cylinder based off of this graph. So here we have our function of two variables, f of xy equals x cubed. It just is a bunch of the same graph just lined up next to each other. Along the y-axis, all these points are critical points because in the x direction they have a zero derivative just because that's how the function x cubed works. But in the y direction, well, the y cross section is exactly the y-axis. And the derivative of a horizontal line like that, is 0. Or you could just go ahead and differentiate x cubed directly and notice that we get 0 for both of them. But the point here is that there is no local maximum or minimum here at all. It doesn't even look like anything really should be considered similar to that. What if we modify it to actually have something with y in it? Let's do x cubed plus y cubed. So we just go ahead and modify this. I'm just going to add a y cubed in there. This one's a little bit more interesting. And it turns out if we do go through the calculations, not too hard to do here, but at the origin at 0, 0, there is a critical point. But again, it's a case where nothing really turns around there. You don't go up to that point and then go down on the other side. We go up to that point and continue going up from there. It does become a horizontal tangent line, or tangent plane in this case, but there's definitely no maximum or minimum there. And as a third example, let's look at y squared minus x squared. So that's a little bit different from the other two. If we go ahead and change this, now we get a surface that looks like this. And if you remember, this is what we called a hyperbolic paraboloid. But at the origin, we do have a critical point. Now you could just find that directly by differentiating, plugging in 0, 0. You should notice that we get 0 for both derivatives. But that point is not a maximum or minimum. There are points near 0, 0 that are higher than it, and points that are lower than it. But this is actually different from the last two, in that if we look at cross sections at 0, 0, there are maximums and minimums of those cross sections. In fact, if we take the cross section, let's do y equals 0 first. If we take the cross section there, it's pretty easy to see that 0, 0 is the top of a parabola. It is a maximum there. If we look in the other direction, where x equals 0, now we see 0, 0 as the bottom of a parabola. So this is a situation where it is a maximum or minimum in one direction it's a maximum, in one direction it's a minimum, but since it's not both the same, we don't have a maximum or minimum of the surface. But this kind of situation is one that we will be able to identify with our test later, and we will refer to it as a saddle point. So a saddle point is a point on a surface where cross sections can either be maximums or minimums, that we can get both of them depending on which cross section we take. In order to identify whether or not we do have a maximum or minimum or a saddle point, we are going to use what we call the second derivative test. Basically, we're going to assume that we do have a critical point, and assume that we have the critical point where we have zeros for both of the partial derivatives. If we have If we have a partial derivative not exist, obviously this is going to fail because we need to be able to take the second derivative, not just the first derivative. But if we do have a critical point where both first derivatives are equal to 0, what we will do is form this expression, d equals f of xx, f of yy minus the square of f of xy. We're going to form that number, and we're going to use that number and to see whether or not we have a maximum or minimum. Basically, if this number is positive, if d is greater than 0 for either a or b, then we either have a minimum or a maximum, depending on whether f of xx is positive or negative. If it's positive, then we have a local minimum. If it's negative, we have a local maximum. If d is less than 0, all it's saying here is that f of ab is not a local maximum or local minimum. In fact, this is when we have our saddle point. And I kind of wish they had it included here. If d equals 0, then it's inconclusive. This would actually be the case in both of the examples that we looked at before. The first and second example here, when we have x cubed or x cubed plus y cubed, both of those are going to have 0 for this d when we actually look at the second derivatives. Before we go any further, I want to mention where this d kind of comes from. I'm not going to go through the proof. I don't really find the proof too enlightening. It kind of feels like you just kind of pops out of nowhere when doing some completing the square. But if you want to look at it, it is in this section on page 1007. But an easier way to kind of recognize what this d is to look at a matrix of the second derivatives of the function. So basically, you could say that the first row is all the derivatives where we start with differentiating with respect to x, and then we do x and then y. Second row, we first start with y, but then we do x and then or y. This is a matrix of the second partials, frequently referred to as the Hessian matrix. And this is actually a really important matrix. Since we're not going to be doing anything more with it, we're not really going to be using it too much here. But if you go any deeper into functions of several variables and how to look at maximums and minimums of these kind of functions for more than two variables, this is definitely the matrix that you end up studying a lot. But the point here is that the d that we have up there is the determinant of this Hessian matrix. If you remember how to take determinants, then we take the product of the first diagonal, so f of xx times f of yy, then we subtract the product of the other diagonal, f of xy times f of yx. But remember, f of yx, as long as we have continuity conditions, and they are assuming here that the second partial derivatives are continuous, then these two values are always the same. This Hessian matrix, as long as we have those continuity conditions, is always a symmetric matrix. We can always reflect it over this main diagonal and get the same results on either side. But that's where this formula comes from. Now, you can actually kind of extend that idea to functions of more than two variables. You can still look at this Hessian matrix. That in that case will be, for a function of three variables, it would be a 3 by 3 matrix. You can look at the determinant of that matrix as well. But we actually need to look a little bit further than just the determinant. So we're able to get away with a slightly simplified version here by being able to look at both that determinant and the value of fxx at that point. In 3 dimensions, we'd have to look even a little bit further. We'd actually have a kind of a more nested condition here, where we'd have to look at the determinant and something else, and then the f sub xx as well. So, not going to go any further. The book doesn't consider anything further than that, but I just want to note that this is kind of just the second step in a far more general result. The first step being the second derivative test from Calc 1. Alright, so I guess one last thing I want to note here, when in cases A and B, where they're testing whether or not f sub xx is positive or negative, we can actually test f sub y instead. In these two cases, then necessarily those two will have the exact same sign. They'll either both be positive or both be negative. And that actually comes from the fact that if they are different signs, then this first term has to be negative anyways, and then subtracting a square can't give us anything. We can't add anything positive to it. So if we started with something negative here by multiplying a positive and negative, we wouldn't get a positive value out at the end. So if d is positive, this first term has to be positive. So both these two second derivatives have to be the same sign. So it looks a little unbalanced, like we're considering x's more than y's, but really we could test both of them, and they just picked x because it's the first one. But usually, because we are already plugging the values into this formula, we'll already have the value of f sub xx, so it really doesn't help us to test f sub y specifically instead. We'll already have both those values. So let's actually put this into practice and look at some examples. So starting with problem 12, they're asking us to find the local maximum and minimum values and the saddle points of the function, and then it wants us to graph it as well, which we might as well do. So f of xy is x cubed plus y cubed minus 3x squared minus 3y squared minus 9x. If we want to find the local maximum and minimums, first thing we need to do is identify the critical points. So we're going to take the derivatives, f sub x. Actually, let's leave out the of x, y. We know that's going to be of that. We differentiate this with respect to x. X cubed becomes 3x squared. Y cubed goes away. Negative 3x squared becomes a negative 6x. Negative 3y squared goes away. And negative 9x becomes a negative 9. We are going to set that equal to 0. But let's actually look at the other derivative first. So we do the same thing except with respect to y. Of course, all three of the x terms go away because you don't have any mixed terms here. Y cubed becomes a 3y squared. Negative 3y squared becomes a negative 6y. And both of these are going to have to equal 0 at the same time. Since I'm going to set them equal to 0, I might as well go ahead and factor them. That will actually help. I'll go ahead and pull out a 3. I'm left with x squared minus 2x minus 3, which I can factor as x plus 1 times x minus 3. Here, it's actually a little easier to factor. We can pull out both a 3 and a y. So we have a 3y times y minus 2. And that's going to have to equal 0. Now, since we don't have anything mixed up here, we only have x's in one and y's in the other, this is actually a little simpler to solve than the more general cases. Usually the trickiest part of doing these kind of problems is trying to solve this system of two equations where we don't necessarily have them be linear equations. So That's not always an easy thing to do. But I'll make sure that like, on the exam you're not gonna run into a problem where that's gonna be really tricky. But just note that it it can be the hardest part of this process. But then from our first equation here, obviously the 3 doesn't really matter, but for this to equal 0, either x has to be -1 or x has to equal 3. For this one, either y has to equal 0 or y has to equal 2. But there's no condition saying that one of these, that it's like the -1 doesn't have to necessarily be paired up with the 0 or with the 2. It can be paired up with either one. So we have to look at all possibilities here. We have -1 with 0, -1 with 2, 3 with 0, and 3 with 2. So we get a bunch of critical points. -1, 0, -1, 2, 3, 0, and 3, 2. And all 4 of those points will give us 0, 0 for our first derivatives. Now let's go ahead and look at the second derivatives. We're going to need to know f sub xx. So we just differentiate our formula for f sub x again with respect to x. 3x squared becomes a 6x. Minus 6x becomes a minus 6. The -9 goes away. F sub y, we do the same thing with f sub y. We differentiate with respect to y again. And in fact, we get a very similar formula. We get 6y minus 6. And then finally for f sub xy, we can actually take either one of these and differentiate with respect to the opposite variable. We'll get the same result either way. But since we don't actually have any y's in the formula for f sub x or any x's in the formula for f sub y, this is just 0. So we'll go ahead and compute d for all 4 of these critical points. Start with 0 or -1, 0. That means we're taking f sub xx at -1, 0. We plug in -1 in for x here. We're going to get a -12. Then we take f sub yy, plug in -1, 0. So 0 in for the y here. We get a -6. Then we subtract f sub xy at that point, but we square that one. And then when we multiply all this together, we get 72. Obviously, that is a positive number. Remember, positive numbers means that we will have a local maximum or a local minimum there, but in order to tell which one's which, we need to look at what f sub xx is, or f sub yy if we want. This time, we already found it. That was -12. That's a negative, and so when we have d is positive and the second derivative with respect to x twice is negative, we get a local maximum. If we look at d of -1, 2, go to the next one. Again, we are plugging -1, 2 into these formulas for our second derivatives. We actually get -12 again for f sub xx, but this time we end up getting a positive 6 for f sub yy. And of course, since we don't have any formula here other than 0, that stays the same. But the point here is we get a -72 instead of a positive 72. And a negative d means that we have a saddle point. And then we just keep going. We have look at 3, 0, and we're going to have to look at 3, 2. And we'll just calculate those values. We'll still have zeros for both of these. In fact, since since f sub y did not depend on x at all, it's gonna be a repeat of the 0, 2 that we had here with the 0, 2 here. So still be a -6 and a 6. And then since f sub xx doesn't depend on y, we're gonna have the same result for both these 3's. But if we plug 3 in here, we get a 12 for those values. So this first one actually gives us -72, and the second one gives us 72. So -72 means we have another saddle point. And positive 72 means we also have to look at that second derivative with respect to x twice at 3, 2, which in this case was a 12. So we have a positive d, positive f sub xx. That means we have a local minimum. So we have two critical points that are saddle points. One critical point is a local maximum, one critical point is a local minimum. If we go ahead and plot those, so our function f of xy was equal to x cubed plus y cubed minus 3x squared minus 3y squared minus 9x. We get this surface here. It doesn't really show everything because we kind of need to scale things out a little bit. Let's see if it will allow me to actually rescale the z-axis so we can actually see things. No, we'll just... Great. But let's go ahead and plot our points. So we had 4 critical points. We had -1, 0, and I'm just going to go ahead and tell it to put in the y value of -1, 0. Or not the y value, the z value. If I plug in -1, 0, that'll give me a point A. Then we have the point -1, 2, and give it the value of the function -1, 2. We have 3, 2, or sorry, let's start with 3, 0, and the value of the function at 3, 0. And then finally 3, 2, and the value of the function at 3, 2. Okay, so for one thing, we can see here why we're not seeing everything. So we can actually see our local maximum at -1, 0. Definitely have that there. Then we can see the saddle point here at -1, 2. But we don't see the other two because the z values are actually pretty big. We have a -27 and -31. Those z values are way down below. So if we actually moved up, or move the picture up so we can see something lower down, we now see our local minimum at 3, 2, and we have a saddle point again at 3, 0. So all the stuff that we predicted to be there is actually there in the places we expected. So kind of nifty. And if it let me rescale the z-axis like I'd want to, then we could actually see all of it all at once. But you can kind of see how we get some really weirdly shaped surfaces, but we can actually go through this process and predict where those significant points are. Let's do another example, this time problem 18. We have a function, it's not just a polynomial this time, we have an e to the minus x in here. We still have the same questions, and we want to see what we can do. But at least this time we don't end up separating x and y from each other. We're actually going to have to deal with x's appearing in f sub y, and y is appearing in f sub x. So it'll be a little bit more interesting. But we start off the same way. F sub x, we take the derivative of this function. We do have to use the product rule here. So the derivative of the first one, the derivative of x squared plus y squared, that's going to be a 2x. Then we just multiply that by the second function. Then we take the first function, x squared plus y squared, and multiply by the derivative of the second function. Derivative of e to the negative x is a negative e to the negative x. So I left that as a negative for that reason. And since everything is multiplied by e to the negative x, I'm going to go ahead and factor that out. And we will come back to doing more with that in a moment. But first, let's find the derivative with respect to y. This one's a little nicer because e to the negative x doesn't have a y in it. So really, that's just a constant, and we're differentiating x squared plus y squared, which gives us a 2y. But then the e to the negative x has to be there. Okay, so both of these are going to have to equal 0 at our critical point, at any critical points that we get. And one thing to note here is that e to the negative x can't ever equal 0. In fact, it's always a positive number. So really, the f sub y equaling 0 means that y itself has to equal 0. Sometimes we have to start with the second one, even though we do want to look at both of them. But once we have that y equals 0, we can use that information in our first one. We can go ahead and plug in 0 for y. And the e to the negative x doesn't matter. So we can go ahead and divide that out. We have that everything that remains is equal to 0. We have 2x minus x squared has to equal 0 for that to work. Now, of course, we can go ahead and factor this, plot an x. And that means that x either has to be 0 or 2. Those are our possibilities. So we have critical points. This time there's only 2 of them because our y value for both of them has to equal 0, but our x value could either be 0 or 2. So we have the 0, 0 or 2, 0. We go ahead and look at our second derivatives. Now, second derivative of this one is, we actually do have to go through the product rule again. I'm going to go ahead and just write out the result. Hopefully you can figure out how to take the product rule and simplify it the way I did. We end up with this polynomial in terms of x's and y's times e to the negative x. F sub y. That one's actually a lot easier because, again, e to the negative x doesn't have any y's in it. So we just differentiate this. The y goes away. We get 2e to the negative x. And then f sub xy, again, we can differentiate either one of f sub x or f sub y with respect to the other variable. I'm just going to go ahead and choose f sub y and differentiate with respect to x because there's not as much going on. But actually, the f sub going the other direction wouldn't be too bad either. But if I differentiate this with respect to x, the 2y is a constant. E to the minus x gives us a negative e to the minus x. So we get a negative 2y e to the minus x. If we look at d at either one of these points, if we plug in 0, 0, remember we do f sub xx first. Plug in 0 here. E to the 0 is 1, by the way. And then if we plug in 0 here, these 3 terms go away, and we're just left with the 2. If we plug in 0, 0 here, we saw that 2, but then the e to the 0 is 1. So we end up with 2. Then we plug in 0 here. Well, actually, y is equal to 0, so that y is going to make everything go to 0. Actually, get a 0 there. And that's square, even though that won't really matter here. Of course, this actually gives a 4. And since that is a positive number, we can either have a local maximum or a local minimum. And we need to look at what is the sign of either f sub xx or f sub yy. But f sub xx, we already found at 0, 0 to be 2. So d is positive, f sub xx is positive. that means we have a local minimum. On the other hand, for 2, 0, we plug, well, we end up with an e to the minus 2 in there. That's just going to have to be there. But if we plug in 2 and 0 into here, well, the y squared goes away. You have to actually calculate what it is for 2. 2 minus 8 plus 4. We get a minus 2. So we have a negative 2 e to the minus 2. For f sub y, we plug in, well, actually, the y value doesn't really matter here, but if we plug in 2, we get 2e to the negative 2. If we plug in 2, 0 into our formula for f sub xy, again, y is equal to 0 here, so we just get 0. And so our result, we end up with a negative 4 times e to the negative 4. The e to the minus 4 really doesn't really matter too much here. It's more the fact that we have a negative number in front of it, because this is always positive. So we have a negative number, and so we get a saddle point. Let's go ahead and plot this one as well. So our function was f of xy is equal to x squared plus y squared times e to the minus x. We get this surface here. We go ahead and plot the points. So we have, what was our first one? 0, 0. And if we plug 0, 0 into this function, obviously we're going to get 0 times e to the 0. We just have the origin. We literally have the origin on this surface. The other one's going to be a little bit more fun, though we can actually let GeoGebra do some of the work for us. We have 2, 0, but then we're just going to go ahead and plug 2, 0 into that function. That gives us a point here, which it didn't really make very dark. So let's maybe make the size of it a little bit bigger so it stands out more. So remember, at 0, 0, we calculated it to be a local minimum, and it definitely is. That's a low point in our surface, even if it may not be the low point overall. Actually, it probably will be. It's probably just asymptotically goes to 0, whereas this actually does actually reach 0 at that point. So it might actually be an absolute minimum for the entire surface. But then we have our saddle point here in the middle. So on one cross section is a low point, but then on another cross section it's a high point. So kind of a nifty looking curve, or surface. I want to do one more example in this video. I know the video is getting a little long already, but I do want to illustrate things. So we're going to look at this function here. It's the same kind of problem, but just a different function. We're going to do exactly the same kind of thing. Kind of move a little bit faster through some of the stuff that we've done a couple times already. The derivative with respect to x is going to be negative y sine x. Derivative with respect to y is just going to be cosine x. And these are going to have to equal 0. So we're looking for that critical point. Of course, that's going to be some work to do. In fact, I actually want to start with s of y again, because it only has one variable in it. If cosine of x equals 0, that means that x has to be one of the places where cosine is 0. It's going to be like pi over 2, 3 pi over 2, and in fact, infinitely many other possibilities. You have to remember some calculus, some trigonometry here. But one thing to note about every point where cosine of x equals 0, if we plug those into sine, we never get 0. Sine of pi over 2 is 1. Sine of 3 pi over 2 is negative 1. In fact, we will always get 1 or -1 from the sign. That means that if y times sine of x equals 0 and sine is not 0, that means that y has to be 0. So using the information we got from f sub y, this can actually show us that y has to equal 0 for every single one of our critical points. So we have a lot of critical points. In fact, we have infinitely many of them. But that's kind of what we expect from a trig function. But all the y values are going to be 0, but the x values are things like pi over 2, 3 pi over 2, all the odd pi over 2's. Now, you might think, well, do we have to plug all those into D? Well, we're just going to make use of the fact that that this is periodic in x. As we put in values of x, it follows a period from 0 to 2 pi, and then just will repeat the same thing. So really we just need to look at pi over 2 and 3 pi over 2. If we look at 5 pi over 2 and 7 pi over 2, they're just going to repeat what we had here. So I'm basically just going to work with these two critical points and just be aware that we have a repetition of these things. We need to look at our second derivatives. Second derivative of f with respect to x, so we're differentiating sine of x again. We get negative y cosine of x. F sub y, we're differentiating f sub y with respect to y, but that's actually a 0 because there's no y's left. And then we have f sub x, y. So again, we can differentiate either one of these. Let's say f sub y is cosine of x, so we're differentiating that with respect to x. We get a negative sine of x. We go ahead and plug in our values. D of pi over 2, 0. Technically, we're plugging it into f sub x, x, but f sub y, y is always 0. It turns out we actually get a 0 here as well, though we don't really need to find that one. If we plug pi over 2 into this x, we have sine of pi over 2 is 1, negative 1, not that that negative really matters, and so we end up getting a negative 1 overall. So this turns into a saddle point. Because our d is negative. If we look at 3 pi over 2 instead, again, f sub y is 0, so we get a 0 there. Turns out this one is 0 as well. We're subtracting what we get when we plug 3 pi over 2 into this x, so we have a negative sine of 3 pi over 2, but sine of 3 pi over 2 is negative 1. So we get a positive 1 here. Again, not that like the sign really matters because we do just end up getting a negative 1 again. So we get another saddle point. And as I said before, if we continue looking at other critical points, we're just going to get a repetition of these same values. In fact, we have infinitely many critical points, but no maximums or minimums anywhere on the surface. We just have a ton of saddle points. If we go ahead and graph this thing, so f of xy is equal to y times cosine of x, we get this surface here. We have a bunch of critical points, so we can go ahead and say put in pi over 2, 0, and that's actually going to give us a z value of 0. So we get a point in there. We have our 3 pi over 2, 0, and we actually get another z value of 0. So we end up getting a bunch of saddle points in there as we go along. But at no point is it a local maximum or a local minimum. In fact, there's definitely stuff that's going up and going down at every single one of those points. So really weird looking curve, or keep saying curve, weird looking surface. You can definitely see the repetition in there. Okay, so I just wanted to illustrate some of the possibilities of what we can have, and kind of see how we actually do. It is can be kind of difficult to do some of the solving. We do have to be sometimes pretty clever about how we solve for our critical points. We'll see a little bit of that in the next video as well, but we actually want to kind of extend what we've been talking about here to, instead of just local maximums minimums, we're going to talk about some absolute maximums minimums. But we'll see some more examples of this process in addition to some other stuff in the next video. So I'm going to leave that here. I'll see you guys then.